Hello. So in this lecture we will look at different aspect of placement, which is an important step in VLSI physical design, and mainly we'll look at two different aspects in this video. That is how we'll basically formally formulate this placement problem, and also we'll look at some of the length estimation techniques that is required to solve the placement problem. Okay. Now, before going into the details of partitioning of placement, let me just quickly recapitulate what we have already discussed in the class. That is, first we discussed partitioning, where we have a large circuit, then we can, using partitioning, we can decompose into a number of sub-circuits with manageable size, which we call as the modules, and we apply some kind of a optimization techniques to do that, and the optimization criteria in partitioning is mainly the minimizing the cut set size. After that, we have done the floor planning, where we have a set of modules and their corresponding netlists, and we optimized in the floor planning stage, we optimized the area of the global bounding box, right? So we get at the output of floor planning algorithms, we get the blocks. That means the modules with the fixed shapes, means the width and height are got fixed up, and then also we also get some approximate locations of the block. But the floor planning stage does not consider any routing area. So we have seen that floor planning solution might be like the blocks are touching each other, right? So there is no space is kept for routing. Routing means to the area where the wires can be laid out, or the interconnection can be laid out. So after floor planning, we can only have some estimate of the layout area, where what I mean by layout area, that only we understand that what could be the approximate functional area. Okay, but we don't consider any area for the routing or wiring. Okay. After that, we have the pin assignment stage, where we define the signal that what the pin will receive, or on the block, on the surface of the block. Okay, on the outer region of the block. Okay, so we can have the pin locations after the pin assignment step, and then in the pin assignment step, there is also some approximation techniques of wirelength calculations, right? And based on that, we actually assign the pin. But pin assignment can be also done can be, if requires it is also sometimes done after the placement. Okay, so I'm not going into the pin assignment step in details. Already we have discussed in the class little bit of that. Now we have the placement. Now we're going to discuss placement. So placement is having a set of blocks with pin locations, predefined pin locations, and you have to place the blocks in the silicon floor area, and such that, so your task is to place those blocks into the silicon floor area such that the total layout area will be gets minimized while ensuring the routability. Okay, so so you can understand this placement is a very important step in VLSI physical design. So if you end up with a poor placement, then your design may take a very larger layout area. In addition, it may result in some performance degradations, right? So in this place, during this placement step, what we during the step of placement, we determine the total layout area of the chip. We consider both the functional area as well as the interconnection area, means the area, the wiring area where the wires can be laid out. Okay. Now when we'll do placement, then we must consider the next step that follows the placement, and that is called the routing. Okay. Now there is some issues regarding the routing step. The one main issue is that there could be limited number of layers that can be used during the routing step, and usually 2 to 4 layers are used for routing, and if we increase the number of layers during the routing, then design cost or the fabrication cost usually go up. So chips with four or more layers are usually having are more expensive to fabricate. This is the inherent limitation of routing, that is the limited number of layers, and because of that, some placement solutions some placement solution may be unroutable. Okay, and that placement solution usually called the bad placement solution. Okay, so which are unroutable. But however, the fact that a given placement is unroutable will not be discovered until routing is attempted. And this leads to very costly delays in the completion of the design. Therefore, it is very important to accurately determine the routing areas in the chip level placement problem. Okay. Now this is the optimization objectives of the placement. Now, the placement must produce a layout wherein all the nets of the design can be routed simultaneously. That means the placement must be routable. As detailed routing information is not available during the placement algorithms optimize the estimates of the routing quality metrics such as the total weighted wire length, the wire congestion, or maximum signal delay. Okay, and now here is an example of the placement problem. So after the floor planning step and the pin assignment step, we have the blocks with fixed shapes. So here all the blocks are like A, B, C, D, and so here we have almost 10 blocks, right? So these 10 blocks has to be placed on the silicon floor area such that there should be minimum delay, there should be minimum routing area, and obviously we have to take care of the total layout area has to be minimized. Okay, now here are two placement solutions are being depicted over here. So one solution is solution 1 and there is a solution 2. Okay, now you can understand visually by looking at this. So here you can see that this pin connections, so here you can see that wherever there is a same pin number, that means they should be connected. So this could be a multi-pin net. Okay, so wherever there is a pin connection, those pin connection has to be connected, right? So in this space, in this pin connections, this wire connections are being approximated by some straight lines. Now obviously you can understand that this solution it's not seems to be good, because there is so many wiring congestion which may lead to a routing problem. Okay, although this pin connections or this wiring connections are being approximated by simple straight line, and usually that is not being done in actual wire length estimation in placement. But even though this seems to be a very bad solution, right? This second solution seems to be a very bad solution compared to this one. And so solution 1 is seems to be little bit better than the solution 2. So this is just a basic idea that how this what is the basic requirement for the placement. Okay, so let me just more formally present formulate or more formally say this placement problem or describe this placement problem. So first we have the input of the placements are basically a set of blocks with well defined shapes, and we have a fixed locations of the pins. Okay, and also we have a net list. Net list means which pin is connected to which other pin. Okay, that description is also known to us. Now the requirement of the placements are find the location of each block so that no two blocks overlap. Okay, so placement should be routable. So unlike floor planning, in placement we keep some adequate space in between the blocks so that the interconnection can be laid out. Okay, so a good placement ensures a subsequent steps of routing easier. Okay, so objective of placement would be minimize the layout area, reduce the length of the critical needs, and also you have to ensure that this the routing should be completed. Okay, so so your placement solution should be routable, and that is very important. Okay. Now, even we can see that there is some after having placement, after getting a placement solution, it may happen that could be some routing related issue. So routing related specific issues, that some of the needs are not being routed, or not routed properly, and you may have to adjust the position of the blocks again. Okay, so that's why it is called a VLSI design cycle. So from the placement routing stage, again you have to go to the placement stage, and again you have to adjust your block positions, and based on that again you have to route the you have to perform the routing. Okay, so that would be so your design cycle time, overall design cycle will increase. So that's why this is important, this placement step is important. Okay, I hope you have understood. Now now more formally, with some notation, let me describe this placement problem. Okay, so with some notation I'm going to more formally formulate the placement problem as follows. So we have, suppose, total n blocks b1 b2 up to bn, a set of blocks which has to be placed. So we are defining like that, we can define like that, and each of the blocks, so bi, so each we are having total n blocks, I is less than greater than equal to 1 and less than equal to n, and each of the blocks are having width and height wi and hi. Okay, so and there is a nets, there is a there we have to define two sets. One set is the set of nets, that is a net list n1 n2 up to nm. Suppose total m nets are there in your design. So and there is total n number of blocks b1 to bn, and all in this, and these pins could be either a multi-pin net or it could be a two-pin net. Okay, it could be a multi-terminal net or it could be a two-terminal net. And also we are defining another set, that is we are calling that is Q. So Q is basically a set of Q is a set of rectangular empty spaces for routing. So this is Q is basically your wiring area. And also we are defining another note in a term that is called Li, the estimated length of net Ni. Okay, and we will see different estimation technique of how we can estimate the Li. Okay. Okay. Now, having said that, now our objective of the placement is to find out the rectangular regions R1 to Rn, okay, for each of the blocks, such that the block Bi can be placed in region R1. Okay. Second objective is to second criteria is to know two rectangles overlap. So Ri intersection Rj should be 5. So null. So right now the placement should be routable. That means Q should be sufficient to route all the nets. Okay, that means the wiring area, the Q is the wiring area, is a set of wiring areas that already we have discussed, right? So that has to be sufficient to route all the nets. And the total area of the rectangle bounding R and Q should be minimized. That means your R plus Q is the total placement, a total layout area. R corresponds to the functional area where the IP blocks or actually your blocks are being placed, and Q is the area which is kept aside for the routing, for the wires to be laid out in this region. Okay, and what we have to do, we have to minimize the total wire length. Our objective is to minimize the total wire length, that is the summation over Li. So Li is the estimated length of net Ni. So it is summation over I equal to 1 to m. Okay, that has to be minimized. And for some high performance circuit, there should be some constraint on the maximum value of Li also. Okay, and that has to be also minimized. So minimizing the summation of Li as well as minimizing the largest Li are both equally important. Okay. Now this general placement problem is considered to be a NP complete problem. Okay, because you can understand, right? So there has to be some heuristic algorithm. So there are heuristic algorithm, just like we have used a simulated annealing algorithm in other problems of VLSI physical design. Here also we will use some heuristic algorithms to find out a best solution, find out a good solution or the best solution over a large solution space. Okay, from a large solution space. Okay. Now the next thing that we're going to discuss is called the wire length estimation for a given placement. Now in placement we have we are basically subject to maintaining the routability that we have already discussed, right? So you have to make sure that the routing should be properly done after the placement. I mean all the nets should be there should be sufficient space for all the nets so that they can be routed or they can be connected. All the wiring can be done. So subject to the maintaining the routability, the primary goal of the placement is to optimize the delays along signal paths. Okay, since the delay of a net directly correlates with the net's length, the placement algorithms often minimize the total wire length. Okay, but the problem is that the actual wiring parts are not known during the placement, right? Because that can be only understand, or that can be only you get to know during the routing stage, right? When you will use different layers for connecting the pins. Okay, so there could be different layers, as just I discussed. So different metal layers, and then the two metal layers can be again connected by via. So there can be some cross connection. If some cross connections comes into the picture, then we use via. So actual wiring paths are not known during the placements, or that can be only so we can only estimate that actual wiring path again. So where again we have to for making some estimation of this wire length, a placement algorithm needs to model the topology of the interconnection nets, and that is basically we call the interconnection topologies. So that is nothing but this interconnection topology, again some graph structure. We again will use some kind of graph structure where the vertices will be the terminals or the pins, and the edges are the interconnections. Okay, and also we'll see that how from a graph structure we can generate a spanning tree, because you know that from a graph we can generate a spanning tree where by covering the minimum number of edges. Suppose if we have a graph with n edges, okay, so suppose I am having a graph with n nodes, and suppose n nodes, then there could be many number of edges, right? There could be infinite number of edges, but we can generate a spanning tree with n-1 number of edges, right? And that is a spanning tree, which spanning tree is nothing but a subgraph of the which is a subgraph of the main graph, which includes all the nodes, right? So we'll use this kind of wire length. We'll look into all those interconnection topologies where we'll use some kind of a graph structure. Okay. Now there are two important issues. There are two important issues in this so we are going to use various types of interconnection topologies, or in other some kind of a graph structure model to estimate the wavelengths. And two things are to be needs to be considered during this wavelength estimation during this placement. Okay, and two important issues are basically whether we have to see that whether it is a 2-pin net or it is a multi-pin net. So, and whether it is a 2-pin net or it is a multi-pin net, and the estimation that you are going to apply, or any estimation model that you are going to employ, that must be applicable to both 2-pin and multi-pin nets, right? And another thing is that, and another important aspect, that how fast a given wavelength estimate can be computed. Okay, that as to also you have to consider, because ultimately you are going to run an algorithm that will run on a machine, that will run on a computer. So if it is very computationally expensive, your estimation technique, then that won't be a good thing, right? So you have to consider that thing also, that the computational complexity. So the speed and the quality of estimation has a drastic effect on the performance of the last placement algorithms. Now now estimation of wavelength of 2-pin nets. And for 2-pin nets, most placement tools usually use the Manhattan distance dm between 2 points, means between 2 pins basically, and we can basically define it by their coordinates. So if we can think like that, it is a grid like structure, and we can define the pin locations by their coordinates, right? So if these two are the points, and their coordinates are x1 and y1, and this is p1 and this is p2, then we can find, and the p2 location is x2 and y2, then we can find out the Manhattan distance between these 2 points by very easily by using this equation, right? So x1 mod of x1 minus x2 plus mod of y2 minus y1, right? So this is very for estimation of the wavelength of 2-pin nets. This is very popular method, or that is often used in most of the placement tools. Now next thing is that for multi-pin nets, we have to use some kind of a estimation model, or some kind of a estimation techniques we have to use. And what are those techniques? Now I will going to describe. Okay, now now for multi-pin nets, the following estimation techniques are used. One is called the complete graph model. Second, we have chain model. Then we can also have rectilinear minimum spanning tree model. We can have rectilinear Steiner minimum tree model. Okay, and also we can have a half perimeter wavelength model. Now, and there are many other techniques. I'm not going to all the techniques, but these are the most of the standard techniques that usually used in wavelength estimation, or in while solving the placement problem. Okay. Now we can understand why this is important. This wavelength estimation important, because then only we can define the cost function, right? Because the estimated wavelength has to be minimized. So that technique will be, so this will be a function that you are going to use. This wavelength estimation technique will be a function in your optimization algorithm. Okay, that you have to. And so for a particular, if you have to use any one of this model in your while you will implement, you are going to solve the placement problem using optimization algorithm. Okay. Now let's start with this complete graph model. Okay, so what is a complete graph model? Suppose I have a pin, I have a p-pin net. Suppose I have a p-pin net. Okay, so p-pin net means a net with having p pins. So here an example with 4 pins, right? So this is one pin. This is, so there are 4 pins are there. Okay, these 4 pins are there. Now and so this is a only one net with 4 pin. So this is a 4 pin net, right? Now your task is to estimate the length of the wire. So when they will be actually connected after the placement, what should be the wire length of this a p pin of this 4 pin net, right? So this is and so in the complete graph model is the estimation technique by which we'll describe this. We'll find out we'll find out what would be the length of the wire. Okay, wire length estimation. We're going to estimate the wire length. Okay. Now in the complete graph model, what we're going to do, so we will find out, so for each pin, so we're going to create a complete graph. That means each pin will be directly connected to every other pin, and they will be connected through their Hamming distance. So not Hamming distance, that is called Manhattan distance. So this you can understand. So there could be PC2 connections. So total P into P minus 1 by 2, total this number of edges. So if it is a 4-pin net, then there will be 4C2, then there will be I guess 6. There will be 6 edges. Okay, for 4-pin net, there will be 6 edges. Okay, so first we'll find out the complete graph model with 6 edges for this 4-pin net. Okay, but the problem is that, but now not a problem, but one thing that you can understand, that is that one thing you can understand, that is called that from this complete graph model we can generate a spanning tree, because there is spanning tree means spanning tree means that you can generate a from this graph, from this complete graph, you can generate a spanning tree with 3 edges. Means there is total 4 nodes are there, so there can be one spanning tree. Okay, there can be one spanning tree with only 3 edges. Okay, and that would be thus and that so basically in the complete graph model we are having so there will be, so if it is a p-pin net, then a spanning tree will contain p minus 1 edges. But in the complete graph, how many edges are there? There are total p into p minus 1 by 2 edges are there. So basically there are p by 2 times. So you are having, in the complete graph model, you are having p by 2 times extra edges. Okay, so basically there this p by 2 is an extra term that you have to normalize, or you have to, there should be some correction factor has to be multiplied. So what we will do, first we will create, so in the complete graph model, what we will do, first we will create a complete for this p-pin net. Okay, for this p-pin net, we will have the location of this pin, right? So we will have the coordinates of these pins. From that we can generate a complete graph model by connecting them. Okay, and we'll find out the Hamming distance between all the nets. So here total 6 edges are there. So total you are not Hamming distance, Manhattan distance again, sorry. So you have to find out the Manhattan distance of all the edges. Okay, so you have to find out the length of the 2-pin, all the 2-pin nets, by using Hamming distance, and you have to sum it up. So this is this part. Okay, and then you will have to multiply this thing with this correction factor, that is 2 by p. Okay, why this is required? Because this is in the original graph model, in the complete graph model, this p by 2 extra terms are being multiplied. So total whatever you will get, whatever you got, so there is some redundancy. So there is some redundancy already there in the total calculated wire length. Okay, total calculated air length, and from that we are estimating the minimum wire length. We are estimating a minimum wire length by multiplying by 2 by p, because already this things is included within the complete graph model, and this p by only p minus 1 edges, only p minus 1 edges are sufficient. Okay, so that's why because in the minimum spanning tree, 2 p minus 1 edges are sufficient, so that's why you are multiplying these things by 2 by p, and we are estimating the wire length of this pp net. So this L net equal to 2 by p into summation over this dm of E, and all the nets are basically E is belongs to all the nets. So here it is total 6 edges. Okay, so you can understand over here that these nets are basically total summation of dm is basically 29. So you can add these things. So you can add this all the Manhattan distance between the pins, all the wire lengths. Okay, you can add up all the wire lengths. Wire lengths are being calculated by Manhattan distance. You can add up all the wire lengths, and that you will end up with 29. And what is the 2 by p factor over here? 2 by p is a 2 by 4. So 29 by into 2 by 4, that means 29 by 2. 29 by 2 means 14.5. So so this way you can find out, this way you can estimate the wire length. Okay, wire length of a pp net. So that is a complete graph model, that is also known as click model. Okay, so steps are, first you have to estimate the wire length. First you have to find out what is the Manhattan's distance between all the vertices. Okay, and then from this summation you will get this summation, then from you have to just multiply by 2 by p correction factor. That's all. Okay, and that then we have the estimate of the wire length. So this is the technique for only for this complete graph model. Okay, now there can be another method, that is called chain model. So in the chain model, this is an alternative model where you can have to connect the pins of a net using a chain topology. Okay, so all the nets, so in this model you have to connect all the pins of a net using a chain topology, and your task would be to find a chain with minimum length. Okay, so here is an example. So same structure, so same net we have considered, that tree which is basically this pin, this pin, this pin, this pin. So this is also a 4-pin net. So same net, just right. And we are finding, we are just find out a minimum chain, a chain with minimum length. Okay, so that means we have to find out a minimum length connecting all the pin connections. Okay, so this is also called it's basically a Hamiltonian path problem, and that is considered to be an NP problem. Though this is simple method, this seems to be a simple method, but it often overestimates the actual wire length. Okay, so there are other disadvantages, that this chain topology is completely changes with placement solutions. Okay, so these two are the main problem of chain model, that is it often overestimates the actual wire length. Okay, but sometime it may give you good result. Okay, but it is not usually a very popular method, this chain method. We'll look at some other methods, that is basically spanning tree based method. Okay, now you can understand what is spanning tree, I guess, right? You can understand from a complete graph model how can we generate a spanning tree. Okay, now the next model is basically RMST model, that is called rectilinear minimum spanning tree model. Now in rectilinear minimum spanning tree model, what we are doing, we are decomposing, we are going to decompose the p-pin net into 2 pin connections and we will connect the P pins with P minus 1 connection. So it is a simply the RMST is simply the it's a minimum spanning tree. So it's going to, we are going to generate a minimum spanning tree. Is a spanning tree with a smallest edge cost, and rectilinear means all the edges lengths correspond to the Manhattan matrix. Okay, so here you can understand that for the same problem we have found out a spanning tree. So this is a spanning tree. So there is basically four nodes are there, 4 vertices are there. So we can have 3 edges, and you can see that there could be many other options. Many spanning tree could be possible for this particular graph. So you can have a complete graph like this, you can have a complete graph model like that, right? And from this complete graph model you can have many spanning tree, right? Now you can have many spanning tree, and out of the spanning tree you have to find out the minimum spanning tree, and that has to be a rectilinear, because we are only considering the edge lengths which corresponds to the Manhattan distance metric. Okay, means we are considering only Manhattan distance while we are computing the edges. Okay, we are not considering any direct connections, like any direct straight line or Euclidean distance rather than that. Rather than saying straight line, it would be a Euclidean distance. All the distances that we are going to consider over here will be simply the Manhattan distance. So that's why it is called rectilinear minimum spanning tree. So from all the options of spanning tree, we have to find out the minimum spanning tree, rectilinear minimum spanning tree, and there are different algorithms are there in the graph theory. You can I hope some of you know the names. That is, one is called the Kruskal's algorithm. Okay, one example of those type of algorithms which can be used for constructing the minimum spanning tree. Okay, so here is an example where the RMST length is 11. Okay, now you can understand this results are being different from the complete graph model. The result, the total click length or total well length is equal to 14.5. In the chain model we found out it is 12. Now in rectilinear minimum spanning tree model it is 11. Right, so RMST length is 11. Now in the Steiner tree, now another optimization can be done. I mean, on the optimization in the sense that another generalization of this of getting the spanning tree can be done by considering the Steiner points in the spanning tree. Okay, so now we're going to discuss what is Steiner tree. So Steiner tree named after J. Steiner. Okay, so it is a generalization of the spanning tree, and in addition to the original node, the Steiner trees have Steiner points. Okay, so edges are allowed to connect to those points as well as to the original nodes, and the incorporation of the Steiner points can reduce the total edge cost of the tree to below that of RMST. Okay, so in the Steiner tree basically we are going to where can branch from any point along its length. Now here you can see in RMST what we have done. So in this RMST we have connected the pins. Okay, and the branching is happening in the pin locations only, right? In the node location only, right? So here in the Steiner tree we can have some branch. We can have some branch even in the where length, anywhere in the where can branch from any point along its length. Okay, so we can instead of joining this thing, we can have a line like this. Okay, and we can join these two lines. Okay, so there can be a branch like this. So this we can do if we want to minimize the well length, or if I want minimize the well length. So Steiner minimum tree has minimum total edge cost over all the Steiner trees, and if constructed in the Manhattan plane using only the horizontal and vertical segments, the Steiner minimum tree is a rectilinear Steiner minimum tree. Okay, so again, why we are calling rectilinear Steiner tree, the that reason is same, that we are only considering the Manhattan distance metric to define the wire lengths. Okay, to define the edge lengths basically, right? Now here in example of Steiner tree. So this is a 3-node. These are the 3-node spanning tree. So this is a spanning tree, right? So this is a spanning tree. So this is a rectilinear spanning tree, but this is not a Steiner tree because we have only connected them, and there is branching, only the branching is there at the node or at the pin locations. Okay, now here in the Steiner tree we can have the branching at any point, and we will do this branching because our objective is to minimize the wire length. So here we are doing this branching. So here we have connected A and B. So same branch is there here also, right? But we are generating we are taking a Steiner point. We are saying that this is a Steiner point or this is a branch point, and we can join these 2 points. Ultimately what we have to do, we have to connect. So this is kind of a so this is kind of a hypergraph also, you can say, but it's not completely hypergraph, but it's rather than hypergraph we should tell it as a Steiner tree, because we're taking a branch along anywhere from anywhere. We're taking this point and we're calling it as a Steiner tree, and from this point we can take a branch to connect the other node. Now the Steiner tree will be also a spanning tree because there is basically all the points, all the nodes are connected. All the nodes are connected, and the length of the also our objective is to minimize the length, and that's why we are considering this type of branching. We are allowing this type of branching so that we can reduce the wire length. Okay. So this is the concept of Steiner tree. So using Steiner tree we can again minimize the length of total wire length to some extent. So rectilinear Steiner minimum tree model, it connects all the P pins of the innet and as many as P-2 additional Steiner points. So a Steiner tree is the shortest route for connecting a set of pins. Okay, and a wire can branch from any point along its length. Okay, so you can understand here it is a Steiner tree for the same net, same 4-pin net. So this is a 4-pin net, and we are generating this Steiner tree. Okay, so you can understand that we are connecting this and this two. Okay, we are connecting this and those two, and we are taking this branch to connect these 2 nodes, and this is going to be and we have to, and there could be many Steiner tree could be possible. Okay, because it only has to satisfy these 2 factors. It should connect all the P pins of the net and as many as P-2 additional Steiner points it can take. Okay, but there could be many Steiner tree, and from this all the Steiner tree you have to find out the minimum Steiner tree where the total number of edges means that the length of the edges. Okay, so that should be shortest. Okay, so you have to find a Steiner tree is the shortest route for connecting a set of pins. Okay, so you have to find out the minimum Steiner tree from a set of Steiner tree. Now I hope you have understood what is Steiner tree and what is the difference between a normal spanning tree and a Steiner tree. So Steiner tree can have some branches along its wires, but in normal spanning tree Okay, in normal spanning tree, we can't have any branch. We can't take any branch from any intermediate points. Okay, along a wire. We can only take the branch. There could be connections between the uh, between two there could be connection between two nodes or two vertices. Okay, or in our case it will be between two pins. Okay. So here the RSMT length means the rectilinear Steiner minimum tree length will be 10. Okay. Now there is another technique of to estimate the wire length, and that is called half perimeter wire length model. Okay. Now in this model, what we'll do, we basically find out a bounding box. So again, we are taking the same example. We are taking the same examples of a 4-pin net. We're taking the example of a 4-pin net, but here the concept is completely different. That we are basically we're going to consider a bounding box of a net with P pins. Okay, so that is the smallest rectangle. So bounding box will be a smallest rectangle that encloses the pin locations, and the wire length is estimated as the half of the perimeter of the bounding box. Now here for this case, you can understand the perimeter of this bounding box. So bounding box is nothing but is the smallest rectangle that encloses the pin locations. So here it is the smallest rectangle. Okay. Now you can find out the Manhattan distance, and you can calculate the perimeter, and your wire length estimation model will be, or estimated wire length will be, half of the perimeter of this bounding box. Okay, and this is commonly used in placement problem or in placement algorithm. It is reasonably accurate and efficiently calculated. Okay, and the reason behind this using this half perimeter wavelength model is that it is more often give you a better estimate for most of the cases, particularly when you have 2-pin or 3-pin nets. Okay, and most of the design consists of this 2-pin and 3-pin nets. So 70 to 80% of all the nets in modern designs are usually 2-pin and 3-pin nets, and this is exactly as same as the rectilinear Steiner minimum tree cost. Okay, so sometimes not exactly, I won't say this is exactly same, but it will be comparably same estimation will get from this half perimeter wire length model, that is called the the half perimeter wire length model actually gives reasonably good estimate it gives for the wire length. Okay, particularly for 2 and 3-pin nets, but if it is more than 2 or 3 pins, means it is equal to 4 or greater than 4, then this HPWL, this half perimeter wire length model, usually underestimates the RSMT cost by an average factor that grows asymptotically as square root of P. Okay, so for 2-3 pins, this half perimeter wire length model is usually will give you a reasonably good wire length estimate. Okay, so these are the few model of or few techniques for estimating the wire length. Okay, so you can understand the most of the techniques are graph topological based. So from the complete graph structure, we can have a minimum spanning tree, and then from that spanning tree we can find out the rectilinear spanning tree, right? And we have to find out the rectilinear spanning tree, and again rectilinear spanning tree can be generalized more by using a Steiner tree, where we can have some branches. We can use some branches along the along its length, along any wire. You can take any branches and you can minimize the wire length a little bit, because often this rectilinear spanning minimum spanning tree RMST model overestimates the actual wire length. So that's why this type of optimization or this type of we have to explore the rectilinear Steiner tree. You have to explore, right? And the problem of rectilinear Steiner tree minimum RSMT is that we have to find out the Steiner tree and minimum Steiner tree, and that is again a NP complete problem, and that is some kind of a difficult thing. And for that, the solution is that we can use some half perimeter wire length model, where basically we estimate the wire length by taking the half of the perimeter, not parameter, half of the perimeter of the bounding box. Okay, so these are the ways we can estimate the wire length, and which is basically define the cost function of the of your placement problem, right? Now obviously we can have a weighted wire length also, so we can use net weights can be used to prioritize certain nets over others. Okay, so for placement P, an estimate of total wire length would be LP equal to summation over W of net into L of net, where each of the net, W of net is the weight of a net and L of net is the estimated wire length of the net. Okay, so if there is there is some critical net is there, and you want to give more priority to certain net over others, then you can define some weightage to every net. So first you have to estimate this wire length by using any of this model. Okay, any of this model, and then you have to multiply this wire length. First you have to find out the length of the particular net. Suppose if it is a PP net, you have to find out you have to estimate the length of the PP net, and then you have to multiply it with the what's called the weight of the net. Okay, and then we can estimate the overall total weighted wire length. Okay, so this way you can define the weighted wire length. Okay, so this is the very so we have discussed. So in summary, you can say that in this video we have discussed how to formally define the placement problem, and how to estimate the wire length of a placement solution. Okay, because we have to define the cost function, and wire length has to be minimized. Total wire length has to be minimized during the placement, right? But we cannot have the actual wire length, right? Because that can be only known, that can be only understand. The actual wiring, it's not known during the placement. That can be only to be known during the routing stage. Okay? That is that will follow the placement stage. Okay, so that's all. and a good placement must be routable. That is also very important. Okay. So let's stop here today, and I will okay, thank you very much.